Okay, hello. This is another worked out problem for intermediate mechanics. And I will let you read the problem, so pause the video for a second. When you're ready, we can solve the problem together. Okay, I assume you've read the problem. This seems complicated. There is a lot of information, but let's see what we can figure out. First thing, we have the total mass of the rocket plus fuel is made up of a lot of different pieces. Okay, so let's call the total mass M. That's going to be the sum of the mass of the fuel of the first stage, plus the mass of the rocket or the engine of the first stage, plus the same things for the second stage, mass fuel 2 plus mass stage 2 plus additional M, which is actually the loads for the rocket. That's the piece we really want to get up to a certain speed. There is a good amount of information here, but really what we have to calculate is the final velocity of the rocket, not so much the how much time it takes for the rocket to get to that velocity or anything like that. So we don't actually need this and that. Those are, in this case, not useful, so we can just ignore them. What we have to use is the expression that gives us the velocity of our rocket as a function of the mass. That the difference between the velocity at time t and velocity at time t equals 0, the initial velocity, is given by the exhaust velocity times the log of the initial mass divided by the current mass. This mass of t, and this is v of t. And in this case, we're interested in what happens at the end of the acceleration phase. So all we have is that for the first stage, v1 is going to be given by just the right-hand side of the equation I wrote, because the initial velocity is 0. And we have the exhaust velocity, m0 in this case is what we call big M. And we divide that by the final mass. So the mass that's thrown away is the mass of the fuel 1. So that's the ratio. And for the second step, second stage, we have an initial velocity that's now v1. Then we have the exhaust velocity 2. And the log of the initial mass now is total mass minus mass of the fuel 1 minus also mass of the engine that is used during the first stage. And the final mass is the total mass minus what's used in the first stage minus the mass of the fuel 2. And that's, as it happens, our answer. That was actually a very simple problem. It looked very complicated, but it wasn't. One thing I encourage you to think about is how do I get the maximum V2? And this is, in fact, a pretty tough engineering problem because you have a lot of knobs. Let's say you figure out that you need this much fuel to be used in stage 1 and this much fuel to be used in stage 2. But the dimension of the engine may depend on how much fuel you need to use. As it happens in real rockets, you would also have to take into account that you need a certain thrust in the first stage to lift from the ground. And if the second stage is still used to get into orbit, well, you still need the thrust to counteract gravity, so you can't make it too small. That influences the mass flows and therefore the engineering of the engine. So the problem is actually not terribly simple. Also, you may wonder, is it going to be better to have 2 stages or 3? Well, that's again going to be the answer to the question will be influenced by how your engine's made. You can make lighter engines. If you build 3 stages, then 3 stages may be better than 2. But if the engines are about the same size, maybe not. You would have to actually crank them up. But for the problem we're trying to solve, this is all there was to it. So thank you, and stay tuned for the next sample problem for our classical mechanics course.